afternoon and welcome back to Elementary Algebra. I am your instructor, Amy Fuchsteiner. We are looking today at Chapter 9. This is the last section we're going to be doing in Chapter 9. It is called Graphing Quadratic Equations. All of Chapter 9 so far has been about quadratics, and so we're going to do one more section, which is how to graph them. And we're going to talk about what the pictures of quadratic equations look like. So in general, the picture of a quadratic equation is called a parabola. And a parabola is a curve that hits either up or down. So this is a parabola facing up. It has several points of interest. The first point of interest is what's known as the vertex. The vertex is the point at which the parabola switches direction. So we're going down, 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 down. And then at some point, the parabola turns and starts rising. This is known as the vertex. This particular vertex or this particular parabola opens up, meaning that it's like a lemur rising to the sun. Right? I'm saying that because it's spring. You can also have a parabola that opens down. So whether you have a smile or a frown, a parabola that opens down would look like a frown. They both have what's called a vertex, right? Because they both have a point or a placement at which they begin to switch direction. This particular parabola was going up, 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 and then at some point it switches and it starts to go the other direction. So your parabolas can open up and they can open down. If your parabola opens up, then your A value is greater than 0. If your parabola opens down, then your A value is less than 0. That's how you tell the difference. For a parabola that opens up, your A is positive, and for a parabola that opens down, your A is negative. What am I talking about? Where am I getting this A from? I'm getting it from the standard form of a quadratic equation, ax squared plus bx plus c is equal to 0. If this A or leading term is positive, we're going to open up. And if that A or leading term is negative, it's going to open down, right? Each parabola has what's known as an axis of symmetry. The axis of symmetry is the line, the vertical line around which the parabola is symmetrical. So everything on the left side here should match up with everything on the right side. It's not going to because I sketched it. This will also have an axis of symmetry where everything on the left side and everything on the right side match. The axis of symmetry goes through the vertex. So the axis of symmetry will go through the vertex, the point at which the direction switches. Most vertexes, or most parabolas, not all of them, but most of them also have what's known as an x and y intercept. So the x-intercept would be on a regular graph. If this is my x-axis, then the x-intercepts are the places where the parabola crosses the x-axis. The y-axis is going to occur where your parabola crosses the y-axis. So in this case, if this is my y-axis, then the vertex is also the y-intercept. Doesn't always happen. We'll see some graphs a little bit later on where that doesn't happen. I could maybe, I can make an example of this one. So in this one, let's see, I'll make the y-axis over here. Let's say this is your y-axis, and let's make your x-axis down here. There's your x-axis. So our x-intercepts would be where the parabola crosses the x-axis, and the y-intercept would be right there. Notice how that's not at the vertex, right? So the x and y intercepts and the vertex and the axis of symmetry. These are the basic characteristics that we look for in a parabola to try and help us graph it. Right? Now, you will sometimes see parabolas in the wild. Parabolas in the wild still have that same basic shape. The McDonald's arches are a great example of parabolas that face down. It's two parabolas next to each other. They have a nice symmetry with each other and then within each other. So that's an example of a parabola in the wild. Some mustaches, I really like this one because I thought this one was kind of funny. But you take this gentleman, I want to say his last name is Cave. He's a musician. Cage. Dave Cage. But his mustache is a parabola. Bananas are sometimes used as parabolas that face up because they have a nice symmetry to them and a nice sort of rounded curve. Falling water, particularly water that comes from a fountain or a sprinkler, is also a really nice example of a parabola. There are all different kinds, and if you look around them, they're used all over the place in architecture, bridges, even in just common nature. They're a pleasing aesthetic. They have a pleasing look to them, that curvature. Here we have two examples of parabolas on actual graphs so that we can tell what they are. Identifying the vertex on this one. First of all, the vertex here is at 2, -1 because we go over 2 and down 1. That is our vertex. You will see x-intercepts. Our x-intercepts are at 1, 0, and 3, 0. Right, those are where the x-intercepts are on that one. This one also has a y-intercept. The y-intercept here is at 0, 3. So we have x-intercepts, we have y-intercepts, we have a vertex. Our axis of symmetry is actually going to go through the vertex. It is a vertical line. Excuse me. It is a vertical line, and it goes through 2. Vertical lines, if you recall, the equation is x equals. So x equals 2 is our axis of symmetry. So that would be our general analysis of the graph. That and the fact that it opens up. But the opening up part we can get from the vertex and from even the intercepts. All right. If we look at our second diagram here, I'm going to zoom in on this one because I'm not sure how well you can see it. You've got vertigo, blink, blink, blink. Don't look. Okay. You might have to go in again. Still don't look. I'm trying to make it more visible. Sorry, I'm messing with this. You might have thought I would have tried better, but yeah, so be it. Okay, got it? All right, let's try our vertex. See how it goes up, 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 up? This is our vertex. That is our vertex. And it is at -1, 5. So -1, 5 is our vertex. Is there an x-axis or an x-intercept? Where does it cross the x-axis? Well, it crosses the x-axis here and here, right? Those are our x-intercepts. X-intercept. Where would those be? Well, it's really hard without knowing more where they are. But if I had to sort of put a place on it, I would say we're at a -3 1/3, 0, for this one on the further left. And this one, I would say, was 1 1/3, 0. So it might not be exact, but it's a pretty decent approximation based on the information and the detail I have in the graph in front of me. So I'm doing the best I can. We have a y-intercept. That would be my y-intercept. And that guy is at 0. I want to go 0 left to right and up 4. So 0, 4. All right. X-intercept is at 0, 4. There is also an axis of symmetry. The axis of symmetry is going to go through the vertex. It's the place where you could like fold the parabola onto itself. I say parabola. Some people say parabola. I don't like saying parabola. It sounds funny to me. So parabola is what I use. This axis of symmetry is at x. Vertical line starts with x equals. And we're at x equals a -1. Notice that that is the x value of the vertex. And that is our axis of symmetry. Okay. So we're going to spend a few minutes determining each part of a graph. Given a quadratic equation, we're going to see if we can determine some of these pieces. So the first thing we're going to look at is the intercepts on a parabola. Now, to find the intercepts on a parabola, in order to find the x-intercept, the key is to let y equal 0 and solve for the x value or values. Sometimes there isn't even one. Sometimes there aren't even one. In order to find the y-intercept, we're simply going to let x equal 0 and solve for the y value or values. Notice we're not going to graph anything. I don't want you to graph anything. We're just going to use the formula itself. So, shall we do the x-intercepts first? In order to find the x-intercepts occur where y is equal to 0. So this means we will have 0 is equal to x squared plus 3x plus 2. We have a quadratic equation. We've just gone through and reviewed 4 different ways to solve a quadratic equation. This is not a perfect square. I cannot use the square root. Is this factorable? Are there numbers that will multiply to give you a positive 2, but add to give you a 3? Yes. So I can factor this as x plus 2, x plus 1. Whoops. Using the zero factor product, in order to get a 0, x has to be a -2 or x has to be a -1. That will zero it out. This tells me that we have x-intercepts at a -2, 0. Where'd that 0 come from? We let y equal 0, so -2, 0, or -1, 0. That's where my x-intercepts are. To find my y-intercepts occur when x is equal to 0. So to find my y-intercept will occur when I have 0 squared plus 3 times 0 plus 2. So when my y is equal to 2, my x will equal to 0, and my y-intercept is at 0, 2. Beautiful. I now know where my x-intercepts are, and I know where my y-intercept is. Let's try it again. I have y is equal to x squared plus 6x minus 7. So my x-intercepts occur. We'll do x-intercepts first. When y is equal to 0. So 0 is equal to an x squared plus 6x minus 7. Okay. This is not a perfect square. I know that because 7 is not a perfect square, so this cannot be a perfect square trinomial. I cannot use the square root function. Is it factorable? Are there 2 numbers that multiply to give me a -7, but when I add them, I get a positive 6? 2 numbers that multiply to give me a -7, but when I add them, I get a positive 6. Because if that works out, this will factor. And indeed, there is. So this will factor into x plus 7, x minus 1. When I multiply a positive 7 and a negative 1, when I multiply a positive 7 and a negative 1, I do get a negative 7. When I add them, I get a positive 6. So this will factor into x plus 7, x minus 1, which means that either using the zero factor product to zero out this first term, my x could be a negative 7, or if I want to zero out the second one, my x would be a 1. So my x-intercepts will occur at a negative 7, comma, negative 7 for my x, y is 0, or if I let x be 1 and y is 0. These are my x-intercepts. The y-intercepts occur when x is equal to 0. So that would be y is equal to a 0 squared plus 6 times 0 minus 7. Whoops, I don't need a parentheses there. So when y is equal to a negative 7, so my y-intercept will occur when x is 0 and y is negative 7. X-intercepts, 2 of them. Y-intercept, 1 of them. 0, negative 7. Okay? That is how you find your x-intercepts and your y-intercepts. We can also determine the vertex of the parabola. And we can determine the vertex of the parabola by using the opposite of b over 2a. If that sounds familiar to you, it's what we square when we're using completing the square. So given a quadratic equation, you can determine your a, b, and c. Let your x value be the opposite of b over 2a and put that in to find the y value. So here we have y is equal to x squared minus 6x minus 9. So we're going to let x equal the opposite of b, so the opposite of a negative 6 over 2 times 1, right? Where am I getting these numbers? All right. This is a, b, c. So my b is negative 6, my c is 9, my a is 1. So that's where those are coming from. So we're going to let x equal a negative 6, which is 6 over 2. We're going to let x equal 3. This tells us that the vertex occurs when I let x equal 3. So if I let x equal 3, then y would be a 3 squared minus 6 times 3 minus 9. So that's going to be 9 minus 18 minus 9, which is a negative 18. I have found the x and the y, so my vertex is at 3, negative 18. When my x is 3 and my y is a negative 18. Without even the picture of the graph, I can use the algebraic formulas to determine where that vertex is going to be. I can at least determine the x value of it. Since that is the vertex, that also tells me that my axis of symmetry will occur when x is equal to 3. That's the additional sort of bonus information that we get from that vertex. Because remember, the vertex also determines where that axis of symmetry is going to be because of the fold. So it's kind of a slick little piece. All right, what about number 4? For number 4, we need to determine our A, B, and C first. I'll do that first this time. So this is our A, this is our B, and this is our C. So x is going to be the opposite of b, so the opposite of 12, over 2 times a negative 3. So that's going to give me a negative 12 over a negative 6. That's going to be 2. So I need to let x equal 2. When I let x equal 2 and put that in, I will determine the y value of the vertex. So this would be a negative 3 times 2 squared plus 12 times 2 minus 7. So a negative 3 times 4 plus 24 minus 7. It's a negative 12 plus 24 minus 7. What's that going to be? 12 minus 7, which is 5. So y is 5. So my vertex is at the xy of 2, 5. The bonus information of this is that my axis of symmetry has to occur in the x value of the vertex. So my axis of symmetry is at x equal 2. What else do I know? Well, that's negative. So this guy opens down. So what that tells me is I'm going to start at the point 2, 5, and my parabola is going to be a frown. That's a down one. Oh, what a downer. Okay. We are going to sketch some graphs without a graphing application or a calculator. We're going to use the parabolas. We're going to analyze for the direction, the vertex, the axis of symmetry, and the x and y intercepts. Okay, we got this. So the same thing we found before. Let's look at this, the direction. This particular parabola starts with a 1x. That's a positive 1. So the direction here will be up. It's going to open up. If you want to, you can draw a little one opening up. We're going to be a smile, not a frown. The axis of symmetry and the vertex come from the same information. So we're going to do the vertex. X is going to equal the opposite of b over 2a. All right. So this is a is 1, b is a negative 6, and c is 8. Okay. I've got those. Perfect. So x would equal the opposite of b. So that's going to be a 6 over 2 times 1. That's 2. So that's 3. So in the vertex, x is equal to 3. So y is going to be 3 squared minus 6 times 3 plus 8. So what do we got? 9 minus 18. That's a negative 9 plus 8. That's going to be a 1. So the vertex is going to be at 3, 1. Axis of symmetry is going to be x equal to a 3. So right now I have a point. I know I have a point at 3, 1. So that's going to be my axis. My axis of symmetry is going to be the vertical line that goes through that. So that's going to be my axis of symmetry. Okay. And I know it's going to go up. So I know it's going to come up from there. All right. So now I need my x-intercepts and my y-intercepts. Okay. X-intercepts. We're going to have 0 for the y is x squared minus 6x plus 8. Right? Right. Okay, so what two numbers multiply to give us 8 and add to give us a 6? Well, that's a 2 and a 4. Oh, I goofed. Here, this should be a negative 1. Why didn't y'all tell me? Right there. I need that at a negative 1. That's what's going on. Okay. All right. So I'm going to factor this. I could use quadratic, but I can factor this. Two numbers multiply to give me 8, add to give me a negative 6. This is going to be 0 is equal to an x minus 2 and an x minus 4. So my x could be a 2 or a 4. So my x-intercepts are at 2, 0 and at 4, 0. 2, 0 is there, 4, 0 is there. Well, that makes sense. That's symmetrical over that. So where's my y-intercept? Y-intercept is where x is equal to 0. So y is going to be 0 minus 0. 6 times 0 is 0, plus 8. So my y-intercept is going to be at 8, and I have another point at 0, comma 8. 0, 2, 4, 6, 8. Now, using my axis of symmetry, since this guy is 3 units from the axis of symmetry, even without going through all the rigmarole, I know I should have another point, 1, 2, 3 on the other side of that, because the axis of symmetry should fold over. This tells me I can draw my parabola. I want my red one. Well, maybe I'll use pink. I'll use this guy. So I know my parabola goes through 0, 8. I know it comes down and goes through 2, 0, 3, negative 1, 4, 0, and it has to come up and hit that one. So without plotting, without chugging different x values in, I'm able to look at these sort of 5 characteristics and determine what this graph is going to look like, or at least a really good approximation of it. Let's try this with number 6. For number 6, we have y is equal to a negative x squared plus 2x plus 3. The direction of this guy, that's negative. So the direction of this guy will be down. This is a frowny one. The vertex, again, the x coordinate of that vertex is the opposite of b over 2a. So I need to determine my a, my b, and my c. The a is a negative 1, the b here is a 2, and the c here is a 3. So the x that I'm going to be using is a negative 2 over 2 times a negative 1, or a negative 2. So the x here is 1. If I let x equal 1, then y would be a negative 1 squared plus 2 times 1 plus 3, and that's going to be 6. So I should have a vertex at 1, comma 6. And since it's at 1, comma 6, 1, 2, 4, 6, that should be my vertex. And that also tells me my axis of symmetry. My axis of symmetry is going to occur at x equal 1. All right, x equal 1. I'm just going to dot this because I don't like making that straight line. So there's my axis of symmetry. Okay, now I need to find my x-intercept. X-intercept. Those occur when y is equal to 0. So I've got a negative x squared plus 2x plus 3. I'm going to multiply everything through by a negative and see if that helps me. 0 is equal to x squared minus 2x minus 3. Can I think of 2 numbers that multiply to give me a negative 3 but add to give me a negative 2? Yep, I can. X minus 3, x plus 1. So in order to zero those out, x would have to be 3 or a negative 1. So my x-intercepts will occur at 3, comma 0 and negative 1, comma 0. So if I plot those points, 3, 0 is there, negative 1, 0 is there. Oh yeah, and that would. Can you see how that would go down? See how that would open down? All right, let's try the y-intercept. Because we can get that point yet too. Y-intercepts occur when x is equal to 0. So that's going to be y is equal to 0 plus 0 plus 3. So 0, 3. There. And if that's the y-intercept, then the axis of symmetry gives me another point, the same direction opposite, the same amount opposite. Okay. So this is not going to be a fun graph to draw. It looks a little squishy. Right? 0, 3. It's probably a little, whoops, that's a little too much. Not the best sketch, but we get it. That's how she's going to work out. I feel like I might be up too far one. Negative 1 squared is 1 plus 2. Yeah, I feel like I'm up too far. Like I made a mistake someplace. Did I make a mistake someplace? I think that's supposed to be at 5. That would make more sense in terms of it. Oh, yeah, because that's a 1 squared negative, not a negative 1 squared. So that should be a negative 1 plus 2 plus 3. So that should be at a 4. There we go. That makes more sense. Fixed my graph. Shouldn't be up there. But that wrong vertex still opens down, still has an axis of symmetry the same. But plotting the wrong point really gave it the wrong look, right? Absolutely. Okay. What about number 7? I think this is the last. Yep. So if I'm looking at problem number 7 here, again, the direction down, right? Negative. The vertex. All right. So for the vertex, I need to know my A, my B, and my C. So for the vertex, x is going to be the opposite of b, so negative 3 over 2a, so 2 times a negative 3 is a negative 6. So this is going to be 1/2. Ooh, okay. The y value is going to be negative 3 times 1/2 squared plus 3 times 1/2 plus 36. This is not going to be a fun number. Calculator. All right. I love a challenge, though. That's what it is. I know they're not fun numbers, but I love a challenge. So I'm going to have negative 3 times 1/2 squared plus 3 times 1/2 plus 36. This should work out, I think. 36 3/4. Okay. So how am I going to plot that? I'm not going to plot anything yet. I'm going to hold off. Okay. I also know where my axis of symmetry is. It is at 1/2. So now I need to know my x-intercepts. X-intercepts occur when y is 0. So 0 is a negative 3x squared plus 3x plus 36. All of those are divisible by 3. So technically I could divide everything by negative 3 if I wanted to make my numbers easier. As long as I divide everything, I'm keeping it even. So 0 is equal to x squared minus x minus 12. Oh, Jiminy, that one factors too. All right, this one does factor, and I can see the factors. But I'm going to go ahead and use quadratic equation on it. Right? So x would equal the opposite of b plus or minus the square root of b squared minus 4 times a times c all over 2a. So x would equal a 1 plus or minus the square root of 49 all over 2. So this is going to be a 1 plus or minus 7 over 2. So x would be 1 plus 7, which is 8 over 2, which is 4, or 1 minus 7, which is a negative 3, or a negative 6 over 2, or a negative 3. So my x-intercepts are at 4, 0, or negative 3, 0. Quadratic was fine, but I also saw right away that this was factorable into x minus 4, x plus 3, which would have given me a 4 and a negative 3 right off the bat without doing all that plug and chug. Just an example of how quadratic formula works, but it's not always the easiest or the most efficient. So, all right. So then we've got the y-intercepts. The y-intercepts occur when x is equal to 0. So if I let x equal 0, then that zeroes out this term, and it zeroes out this term, and it just leaves me with 36. Okay. So if I'm looking at this graph and I'm trying to graph what's here, I know it comes down. I know it opens down. I know I have intercepts at 4, 0. That's 4, 0. And negative 3, 0. There's negative 3, 0. But I have a vertex at 36. And 36 is going to be way up here. My axis of symmetry is at 1/2, which is technically going to be down the middle here. That's my axis of symmetry. I have a y-intercept at 0.36. 0.36 is going to be up, and then it's going to go at 3 and 3. Oh, man. So if I had to graph this, given the graph that I have, I mean, basically what I could say is that this is going to be nearly a straight line up. And then I'm going to come down, and it's going to be symmetrical, but, I mean, it's got to sort of mimic that. But this is all I'm going to see on that graph. I do know where it's going to turn. I do know where the y-intercept is, and I do know where the vertex is. But I cannot graph them on this particular graph. That makes things a little bit harder to do. This is one of those cases where you would want probably a graphing tool, actually, to help you with it, just to check, at least at the end. So, all right. We've done all of that graphing without a calculator. For this particular reason, you can solve your quadratic equations using the picture. The picture does help you to solve. Basically, the x-intercepts on your graph will give you the solutions. It's sort of right? Because remember when we solved all of these guys, we could solve them by factoring. Do you remember that the factors give you the solutions? And then we use those solutions to find the x-intercepts? So, if you have the actual picture and you know where the x-intercepts are, they can give you the factors, which are the solutions anyway. The x-intercepts are the roots of the equation, and those roots of the equations are your solutions. It's like great. So when you're looking at the quadratic graph, when you're looking at the graph of the parabola, you basically have 3 options. You could have 2 solutions, which is what we know, it's what we look for when we have a degree 2 polynomial. You could also have a single solution. This is called a touch and go. It basically means that your x-intercept touches and leaves again. Your vertex is on the x-intercept. And the third option is that there are no solutions. And if there are no solutions, then you will not have any x-intercepts at all. So it means it will not cross the x-axis. All right, let's look at some of these problems. We are going to use these graphs to determine if the parabola has 1, 2, or 0 real solutions. If there are solutions, we're going to list what those solutions are. All right. There we go. Graphs are small, but I'm zooming in. Okay, so if we look at this first graph, you see that there are 2 x-intercepts. So the 2 x-intercepts mean that there are 2 solutions to this. Those solutions are at the x-intercepts. Those x-intercepts are there and there, or x equal to a -2, or x equal to 1. Our intercepts are -2, 0, and 1, 0. Those intercepts, the x values, are the solutions. Let's try the second problem. If we look at problem number 9, in problem number 9, we also have 2x intercepts. Those 2x intercepts are at 9, 0, and 18, no, oh, that's 6, 0, sorry, 6, 0, and 18, 0. This tells us that there are two solutions to this parabola, and they are at x equals 6 and x equals 18. If we're looking at problem number 10, problem number 10 also demonstrates a parabola that opens down. We have 2x intercepts. Oh, I forgot my x. 2x intercepts. We have them at -21, 0 and at 14, 0. This tells us that there are two solutions. Those solutions occur at x equal -21 and at x equal 14. With problem number 11, we see a slightly different, we see a slightly different outcome. With problem number 11, we only have one intercept. This one intercept is at -4, 0. This tells us there is only one solution to this quadratic equation. It is known as a touch and go, and that is because basically the graph just touches the x-axis and then moves along. This is one solution at x equal to a -4. Right? One solution at x equal to a number -4. This is also known as a double root or a double solution. Okay, let's look at two more. Problem number 12. This particular parabola opens up. We have 2x intercepts. Those 2x intercepts are at, 2, 0, and 10, 0. This tells us that there are two solutions to this parabola. Those two solutions are at x equals 2 and x equals 10. Lastly, when we look at problem 13, here we have 0x intercepts. At no time does this cross the x-axis. You see how it's all above? Here's our x-axis. At no time does it cross. There are 0x intercepts. This tells us that there are 0 solutions, or that this problem is no solutions. I can't write there. There you go. In all likelihood, the solutions may very well be imaginary, meaning you get the square root of a negative number here. So, okay. All right. Hopefully you are now able to do a bit of graphing without actually ever having to plot an XY table, which is exactly what we want you to do. And you have some background in analyzing the different characteristics of the parabola. If you have any questions or concerns, again, feel free to reach out to me. I am here to help. And the Math Center is also at your disposal. Julia and everyone in the Math Center wants to see you succeed just as much as I do. All right. Thank you so very much. And you all have a good night. Bye-bye.